Welcome back. Today, we're initiating a deep dive system diagnostic into a truly fascinating piece of technology. Our main objective for this explainer, we are going to decode a critical military-grade networking protocol known as RFC 6621. Now, I want you to imagine, just for a second, trying to shout a message across a packed, incredibly noisy room. But here's the catch. The crowd keeps moving. People constantly lose sight of each other. And if every single person who hears your message just blindly shouts it out again, you risk completely drowning out everyone else. Well, that right there is the massive, almost mind-bending engineering hurdle that military and emergency mesh networks have to face every single day.
All right, here is our tactical roadmap for this explainer. We're going to kick things off with the wireless broadcast storm, then we'll map out the SMF architecture, look at catching duplicates, explore the relay set solution, break down a nasty little vulnerability called the Wormhole Pre-Play attack, and wrap up with some tactical real-world integration.
Okay, part 1. The wireless broadcast storm.
To really set the stage here, we need to understand exactly why your traditional wired network solutions completely fall apart when you push them into dynamic, unpredictable environments. Think about it. How on earth do you efficiently get one piece of data to multiple recipients across moving, unstable radio networks without the whole system just collapsing into static and noise? This is literally the core challenge of MANETs, or mobile ad hoc networks. See, in a standard wired network, you can build these really elegant, stable trees to route your data. It's predictable. But when your network backbone is made up of mobile radios pinging intermittent links, yeah, those trees just snap. The network is constantly having to rearrange itself on the fly.
Enter the U.S. Naval Research Laboratory. Back in May 2012, their team provided an incredibly robust answer through the Internet Engineering Task Force. They published RFC 6621, which stands for Simplified Multicast Forwarding, or SMF. Now, it's officially classified as experimental, but let me stop you right there. In IETF terms, that absolutely doesn't mean it's untested or flimsy. Not at all. It means this is a highly vetted, highly specialized handbook built specifically for extreme tactical deployments. We aren't talking about a universal standard meant for your living room Wi-Fi router. This is heavy-duty engineering.
Moving right along to part 2, inside the SMF architecture.
So how does it actually pull this off? Let's pop the hood, shall we? The SMF router basically operates on a 3-part modular circuit. Step 1 is neighborhood discovery. It has to figure out exactly who is directly around it, usually leaning on another protocol called NHDP to locate its 1-hop and 2-hop neighbors. Step 2 is relay set selection. This is essentially the brains of the whole operation. It calculates precisely which of those nearby nodes should actually be allowed to retransmit the packets. And finally, step 3 is the forwarding process. This is the engine that executes the packet handling. It receives inbound data, checks for duplicates, and forwards it based on whatever step 2 decided. And the brilliance here? By keeping these 3 functions totally separate, engineers can upgrade one single part of the system, like, say, swapping in a completely new relay algorithm, without having to rip out and rebuild the entire engine from scratch.
All right, part 3, catching duplicate packets.
Let's zoom in on our first core mechanism inside that forwarding engine. Look, if we don't catch duplicate packets in a mesh network, these radios are literally just going to endlessly repeat the exact same data back and forth until the entire system completely dies in what's known as a broadcast storm. Not good. To stop this, the protocol uses 2 types of telemetry readouts to detect duplicates. First up is IDPD, which relies on identification tags already stamped onto the packet, like an IPsec sequence number. But if a packet doesn't have a reliable ID, well, that's where HDPD steps in. Instead of looking for a simple tag, it acts like a complex digital fingerprint scanner. It calculates a unique hash based on the actual contents of the packet itself.
And that fingerprint scanner, it spits out a very specific number, a 160-bit SHA-1 digest. Now actually, let me clarify something really crucial here. This 160-bit hash is used purely for uniqueness. It is not for cryptographic security. It's just a highly mathematical, incredibly fast way for the router to say, yep, I have absolutely already seen a packet with this exact payload, which allows it to instantly drop the duplicate and save precious bandwidth.
But here's the really cool part.
The engineers at the IETF didn't just try to recycle old ideas to make this work. They actually had to invent a brand new formalized component for modern networks. See, standard IPv6 doesn't have a built-in packet ID field the way the older IPv4 did. So RFC 6621 actually defined a completely novel IPv6 extension header called SMF_DPD. It's a fully registered, bit-level wire format engineered from the ground up specifically to carry these duplicate detection fingerprints across a tactical mesh. Pretty amazing, right?
Which brings us to part 4, the relay set solution.
Okay, so once you stop the duplicates, you still have to figure out who actually gets to transmit the fresh data. The engineering rationale here is pretty straightforward. To quote the RFC text itself, classic flooding comes at the expense of additional network overhead incurred from unnecessary packet retransmissions. Basically, classic flooding, where every single node blindly repeats every message it gets, is super easy to implement. But having everyone in our moving crowd shout the message all at once, it's a catastrophic waste of battery power, processing, and radio spectrum.
So, the million-dollar question is, how do we actively reduce the number of people shouting? The answer is a brilliant graph theory concept called a connected dominating set, or CDS. Let's go back to visualizing our moving crowd. Instead of handing everyone a megaphone, we authorize only the most strategically placed individuals to use one. We are essentially calculating the absolute smallest possible group of interconnected people required, so that every single other person in the crowd is standing right next to at least one megaphone. Boom. That is your optimal relay set.
Now, the protocol gives you 3 distinct flavors for figuring out exactly who gets those megaphones. ECDS uses a self-election process, so the most senior node in a 2-hop radius essentially steps up and says, "I'll take the job." SMPR is a bit different. Here, each node personally handpicks a few trusted local neighbors to relay on its behalf. And finally, MPR-CDS is a hybrid, blending that local selection with a mathematical guarantee of network-wide reach. Because real engineering is always about choosing the right trade-offs. These options let operators perfectly balance calculation speed with how fast the overall network needs to adapt to physical movement.
All right, moving into part 5, the wormhole pre-play attack. As robust as this architecture is, no system is perfectly impenetrable, for sure. And to their credit, the IATF authors honestly and transparently documented a major security vulnerability right there within their own framework. It's called a wormhole pre-play attack, and here's exactly how it unfolds. At time 0, a bad actor uses a directional antenna to eavesdrop on packets from way across the network. By 10 milliseconds, they artificially lower the packet's time to live, or TTL limit, and quickly inject this modified clone back into the mesh. At 20 milliseconds, a target SMF router gets the clone and logs its fingerprint in its cache. Then finally, at 50 milliseconds, the legitimate packet arrives through normal relaying. But the router checks its cache, thinks, "Oh, I've already seen this," and silently destroys the real valid data. It's incredibly sneaky, a low-cost, high-damage attack.
But the authors didn't just point out the flaw, they engineered a really elegant countermeasure. The fix? You just cache the TTL value right alongside the packet fingerprint. So, if a packet arrives that looks like a duplicate, but its hop limit is actually higher than the one stored in the cache, the router instantly realizes something is fishy. A higher TTL means it traveled fewer hops than expected, which is a massive red flag signaling that the earlier duplicate was probably a spoofed fake. The router immediately overrides the cache and pushes the legitimate data through. Problem solved.
And that brings us to part 6, tactical real-world integration.
Let's enter our final diagnostic phase here, because we need to see how this experimental framework actually connects to the wider internet and the physical battlefield. SMF domains, they aren't just isolated bubbles. They rely heavily on sophisticated border router gateways to safely translate data to and from the standard wired internet. Think of these border routers as the bouncers of the mesh network. They enforce administrative scoping rules so local, sensitive traffic doesn't accidentally leak out. If you have multiple border routers injecting the exact same external data, they slap on special tag-grid labels, so the mesh can still catch duplicates accurately. And most crucially, they use proxy filtering. This ensures the mesh only receives external internet streams that a node inside actually specifically asks for, entirely preventing the mesh from being flooded by outside internet noise.
And if you're wondering if this is actually used, here is the absolute, undeniable proof of deployment. The U.S. Naval Research Laboratory actively maintains a public open-source reference implementation of this exact architecture right now on GitHub under the name NRLSMF. The techniques detailed in RFC 6621 have been physically validated in real-world ground-to-UAV drone mesh network field tests. They've also been demonstrated in complex multi-gateway environments at the IEEE Military Communications Conference. This protocol isn't just some theoretical academic exercise on paper, it is the tactical reality of modern mobile networking.
So, as we wrap up this explainer, I want to leave you with kind of a provocative thought. RFC 6621 is so successful precisely because it doesn't try to force rigid wired network habits onto a chaotic wireless reality. It just accepts that in a moving crowd, some level of data flooding is completely unavoidable. The real question it asks is, how do we make that flooding smart? As drones, autonomous vehicles, and emergency responders increasingly rely on these dynamic moving mesh networks out in the real world, how will the next generation of engineers push these algorithms even further? It's a massive challenge. Keep exploring, keep learning, and I'll catch you in the next explainer.